The next set of derivatives we're going to look at are trigonometric functions. We're going to mainly focus on sine and cosine, and they're quite easy to remember. But before we start, it's important to note that the derivatives only work when your angles are in radians, which means if any derivative questions will come through you, then you should know that the angle will always be in radians. So the derivative of sine is cosine, and the derivative of cosine is a negative sine x. One thing to note in case you're not sure, because this is not a common notation used for students, but it is something you should know. This notation is the same as deriving. So if I said y equals to sine x, so this is a side thing just to talk about notation. I could say dy by dx if I wanted to. So I could say dy by dx. I can also say instead of y, well, y is basically sine. So I can say d sine of x over dx. So it's like, oh, instead of me saying y, let me actually tell you the function that I want you to derive. So instead of y, I'm going to write sine of x. They're both the same thing. So this is a function and this is a function, but instead of writing the symbol y to represent them, I'm going to actually plug in the whole function here. So it also works if you have something like y equals to 3x plus 2. I could say dy by dx. I could also say, well, can you differentiate 3x plus 2 with respect to x? So it just works the same thing. Let's just talk about notation. I could have easily replaced this with f of x, but it's good to be exposed to different types of notation for derivatives. So a couple of these examples, and then we're going to develop the examples. So if I have 5 sine of x, I can split the 5 as a coefficient. That's something we've done before with exponentials and logs. And then I'm just going to derive the sine x. So that's going to be cos of x. And then I'll multiply the derivative with the coefficient. So that's 5 cos of x. And then I'll just remove the brackets. So you can easily move from the first line to the last line. Just keep the 5 on the side and then differentiate the sine x to a cos x. And then I could do like a combination of derivatives. So again, doing the same thing, kind of taking the coefficient on the side and differentiating the trig functions themselves. So the sine x becomes a cos of x, and the cos x becomes a negative sine x. Be careful with the negatives. That's why it's a good idea to put things in brackets. And then if I simplify this, I'm going to get 2 cos x plus 3 sine x. Again, you can start from the first line to the last line. You can put the 2 on the side, say sine x is cos x. And then put the negative 3 on the side, say cos x is negative sine x, but just be careful with the negative. So just careful with the cos x because the derivative is a negative. Now what if the argument, so again defining what an argument is, whatever's inside the sine or the cos, we call this the argument. So what if the argument was this complex function? So it wasn't just x, it was like something more. Well, what you're going to do is similar to the chain rule. It's actually the chain rule, but we're just going to simplify it saying this. So if it's for sine, then you're going to take the derivative of the argument, so this is the derivative of the inside, and multiply it by cos, and then keep the u of x there. And if it was cos, if the function was cos here, you're going to derive whatever was inside. So negative u, you're going to do the derivative, which is u prime, then the negative sine u of x. It's going to make sense with an example. This is just a lot of words here. So let's say we have f of t is equal to sine root of t. And so I can rewrite the t as the root of t as a power of a half. And then I'm going to derive it. So what we're going to do is, this is the derivative of the argument. So t to the power of a half will be a half, t to the power of a negative a half. That's something you would know already. And then this is the derivative of sine. Sine becomes cosine, and you'll keep the same argument. So you won't change the argument. But you've derived the sine already. So then I'm going to simplify it. The negative a half becomes a root in the denominator because of the negative. So we end up with this simplification. So, and you can keep it as it is. Obviously, the root of t's don't cancel because one is an argument of cos and another is in the denominator. This is another example. So I have this function, and as you can see, the argument is quite this complex function on its own. So we're going to do the same thing. We're going to have the derivative of the argument. So this is the final answer. So what I've done is I've taken the derivative of the argument, which is 4x minus 7, and I've multiplied it by the derivative of cosine. So the derivative of cosine is going to be negative sine, and then the argument stays the same. So then I can simplify it. I'm just bringing the negative to the front, because the negative from the sine to the front, because everything's being multiplied. Remember, everything's being multiplied here and here. So I'm just going to bring the negative to the front, which is why I've used this kind of complex notation. This negative actually belongs to the sine, not belongs to the sine, belongs to both of them, but it came from the derivative of cosine to negative sine, but we put it at the front for convention. So next we are going to move on to more complex examples. So we are going to use the chain rule now. Well, these two are technically the chain rules, but we're going to even explore it further. So we have f of x is equal to cos squared of x. So in this case, it's going to be, I'm going to rewrite it as cos x. I'm going to put the power of 2 outside, but these two are equivalent notations, just to be aware. So I can say u is cos of x, and then f of x is equal to u squared. And then I can use the chain rule, dy by dx is equals to dy by du and du by dx. This is not the notation I should be using. I should be using f of f prime, but I just want to use this because this is the conventional chain rule that I've been using in all of the videos. So just a note on notation. So the derivative of the f in this case, so the green function, is going to be 2 times u, and that will be multiplied by the derivative of u, which is a negative sine of x. So that's going to simplify to negative 2 cos x sine x, because the u is basically cos of x, so you bring back the substitution. That's going to be a negative 2 cos x sine x. Go back a few seconds if you need to rewatch what I did, but it's still basically the chain rule. And then I can rewrite this using trig identities. Go back to trigonometric identities. You can find them in your data booklet as well. At 2 cos x sine x is basically sine 2x, and then I could just plug in the negative at the front. If you want, you can use trig identities, but they will be helpful. So using the identities, sometimes they do make your life easier. So if I have f of x equals to 2 sine x cos x, you can use the product rule here in order to differentiate this. But if you have the data booklets with you, then the f of x is basically 2 cos of x. So it's an equivalence here. And then I could use one of the rules in there, which is the derivative of the inside, which is 2. And then multiplied by the derivative of sine, which is cos, and then keep the argument the same. So this is much easier than actually using the product rule. But what if we have to use the product rule? So let's say it's just sine x cos x. Notice the difference. On the previous slides, it's 2 sine x cos x. In here, it's sine x cos x. So it's not a 2 sine x cos x. So I can't use the trig identity. In this case, we do use the product rule. So the original, which is sine x, the derivative of the second function, which is a negative sine x, so I'm putting everything in brackets, and then the derivative of the first function, which is cos x, and then the second function is cos x. And then I just simplify these. So the first is going to be a negative sine squared x, and the second is going to be cos squared x. And then again, using some of the trig ratios, this is going to simplify to cos 2x. So that's using the trig ratios if you want to. The trig ratio for this one is commonly written as cos squared x minus sine squared x. That's going to be cos 2x. So these will be helpful either in simplification or in the beginning. So what if we have to use the quotient rule? So in this case, best example to go for is tan of x, for two reasons. One, we're going to practice the quotient rule. Second is it's good to know the derivative of tan. So if I rewrite tan, so this is the tan identity, this is sine x over cos x, and then I'll use the quotient rule. So using the quotient rule, I'll have the denominator cos of x times the derivative of the numerator, which is cos of x, minus the numerator sine of x times the derivative of the denominator, which is negative sine of x, divided by the denominator squared. So we have all of this. I'm going to simplify it, and that's going to be cos squared x plus sine squared x over cos squared x. If you want to simplify it, that's up to you this way, as in splitting the fraction. But an easier simplification is to know that the numerator simplifies to a 1, because the numerator is basically the Pythagorean identity, cos squared x plus sine squared x, not minus. The minus is a different identity. So that's 1 over cos squared x. If you're doing math HL, then that would be a, you can use one of the reciprocal functions to rewrite this. So hopefully the video is helpful. Make sure you go back to the basics. You start with the basic derivatives of sine and cosine. Just remember to use all the rules correctly and use any trig identities that might be helpful.